调好了，那个调好了。OK。还有1分钟啊。我们这个课在日本也上，所以我们走了。那稀里哗啦是他们那边的声音是吧？
对对，小故事。
OK， 他们那边 settle down 啊。Okay, let's start. Today, we're going to talk about this confidence limit. The confidence limit is also known as confidence interval. Are they ready? The Japanese, the Tokyo side, are you ready?
Yes.
Yes. Okay. Okay. All right. The confidence limit is also known as confidence interval. It's actually established from a ensemble average and the distribution of the data points. So this distribution of these data points, this random variable can be generated through various methods and different criteria. Yeah. And here today we will demonstrate one way to establish this confidence limit or interval. Typically, when you see data, you will see the data like plotted in the bar charts and with a little line interval indicating on top of that. And this little line actually indicate how well and how tight the distribution is. This is the mean and this is the scatter. This is the mean, the scatter. So this is what we call the confidence interval. Yeah, it's through many different many different data and the distribution of this data. There are different ways to plot this. For example, you can also have a mean look like that and a confidence interval as a band. And this band has statistically there are two different ways to divide, point-wise or simultaneous. A point-wise means each point you establish that. Simultaneous means this interval will cover everything. Yeah, cover all the points. So there are various ways to actually give you a confidence interval, and that why we want to do that. The reason is that as we have already presented here, the EMD, the empirical mode decomposition, can generate infinite many sets of data. Now, which set is good? We don't know, right? So in this case, so one of the infinite many sets, they really represent the true physics. How do we know it represents the true physics? So to answer this question, we have to establish a limit. So within this limit, 99% or 95% of the truth is actually happen within this interval. Yeah. So that's why we need the confidence interval, because our answer, the so-called uniqueness, is within the selected parameters. But the parameters, if you change the parameters, you generate another one. Now, how do you know the other one is better than this one? Which one is the best? Which one is the truth? It's an unknown question. So we have to establish that. Now, traditionally, traditional method has the similar problems. Even Fourier analysis, for example. The Fourier analysis is sine cosine. Yeah. Well, how do we know that the sine cosine is best? Or even within sine cosine, how do we know this spectrum actually represents the true spectrum? Yeah. And so we have to try many times. And this many times is the so-called ensemble average. Ensemble means the true ensemble is hard to achieve. True ensemble means you have to try every possibility independently. But who has all the time to try all the possibility? So we will have to infer this, the truth within the limit of the data that we collect. Wavelet is the same thing. How do we know the wavelet you select is really good? Yeah. And what if I change another wavelet? Then I will get another answer. So different wavelets will give you different answer. It means the answer you got depends upon the tool you use. So it's not physics, it's mathematics. Yeah. So here we claim that we represent physics. Then how do you know that the physics you represent is good? So we have to establish this limit. So when we look at the confidence limit for Fourier spectral analysis, the confidence limit is actually not most of the confidence limit is not generated by the ensemble average. Right? It's actually generated through ergodic assumption. What is ergodic assumption? Ergodic assumption means if I have a data, then this data has to be stationary, of course. Now, under stationary assumption, with a very general assumption of independence and whatever, then we say that this data, the average, the ensemble mean, which we cannot get, but the ensemble mean is very close to the temporal average, spatial average, or temporal average. So instead of getting the real true ensemble average, we take the time series, we take each section, we take different sections, we average different sections and get the mean. So the ergodic assumption generates the ensemble for us in Fourier analysis. Now, so instead of ensemble, it divides the data into M section, into a number of sections. M can be 3, can be 5. The more, the better. Okay, but each section that you choose, the more section you choose, then each section the data is shorter. Then the resolution getting poor and poor. So there is a trade-off. Yeah. So this M section average is represented as ensemble average. Yeah. This therefore for Fourier analysis, the confidence limit is built based on linear stationary assumption, yeah, and also based upon the subsection is statistically independent. Yeah. The independency is very difficult to prove exactly. Now, the simplest way is to compute the correlation, but the correlation does not imply independence. By dividing the data into subsections, the resolution suffers. We know that the Fourier analysis, the resolution depends upon the data length. The smallest division of frequency is 1 over total capital T. Yeah. So if you take the shorter data, the resolution gets poor and poor. Yeah. So there are two very important numbers in Fourier analysis. One is the data length, the other one is the sampling rate. Sampling rate determines the highest frequency. The data length defines the lowest frequency. So within the high and low, you get the resolution. So statistical independence means that the germ probability of the sample are totally uncorrelated or independent means they are orthogonal. So independence variable are uncorrelated, definitely uncorrelated. Yeah, but uncorrelated may not be independent. See, for example, we'll demonstrate the confidence limit based on this simple data here. Now, if we take this data, we do a Fourier transformation, you don't get just one answer. You get many, many answers. Depends upon how you handle the data. If you take the whole data and put it in a Fourier transformation, you get this. This is this. This is the full data that you got. You see, now you get a very sharp peak here. This sharp peak there actually is the annual cycle, and then a half annual, and then you also get a very steep monthly. Yeah. Monthly and the harmonics. But then this, you don't have any confidence. You don't know how well the answer resides. So if you divide the data into 7 different sections, each section consists of 2,480 points. If you're doing that, and this 7 sections give you almost 14,000 data points, non-overlapping. So if you take that 7 sections, then you get 7 answers. The 7 answers give you a mean, which is the blue, and give you the standard deviation. Yeah, 1 sigma above, 1 sigma below. Typically, 1 sigma above and 1 sigma below represents 67%, 65% of the answer. So now you see that this peak widening up. That means you don't have the frequency resolution as you had before. However, this gives you a limit. So, well, this peak cannot be more than that within the 66% of the answer. So each point has a limit. This gives you confidence. Yeah, if I get this, I'm pretty comfortable because most of the data will be within this. But here, you don't know. Yeah, it's sharper, but you don't know. And especially when you look at this gives you lots of information. But exactly, is this significant? Is that significant? You don't know. Yeah. But if you get here, then you are relatively comfortable about the value that you got. Yeah. So this is the confidence limit in the Fourier spectrum. So we don't know whether the subsections are statistically independent. Especially when people do Fourier spectrum, they use subsection. They do not use subsection totally separate. They actually overlap almost half of that. So if your half section is overlapped, so it cannot be totally independent. Yeah. So so this is the problem that we have. Now, for confidence limit for Hilbert spectrum, the problem that we have is this: so any data can be decomposed in infinite many different component sets. EMD is a method to generate infinitely different ways. Yeah, by changing the parameter, for example, the stoppage criteria and all that, you actually have many different IMF representation. Yeah, based on different parameter. Of course, some of the IMF are better than others. Then we have different ways to judge which one is better or which one is not as good. Yeah. Now, the way to judge this, which one is or is not valid, there are many ways. So I, for one, use orthogonal index very often. If my decomposition is not orthogonal, I will be very worried. Yeah, I will try different ways to get it orthogonal. Yeah. So the orthogonal index is a very good way to judge the decomposition, whether the decomposition is good or bad. Now, a confidence limit can then be based on ensemble of the valid IMFs. So if you use different criteria to generate the IMF. Not all IMF are valid. For example, if we use orthogonal index, we find some are totally unorthogonal. Then we discard that. We keep the ones that are good. Then we average this. We will get it. So here, in this particular case, I'm going to use the S number as a criteria to generate this different IMF sets, and then use that as a as the base to build the confidence limit. The nice thing about this IMF approach is that this seems to work for nonlinear, non-stationary data. In non-stationary data, you cannot subdivide into different sections. If you divide the different sections, they are totally different. Yeah. So then you cannot average them together anymore. So, so this is the way we're going to do confidence limit. A different kind of confidence limit for IMF, for EMD, we can also implement that. For example, we can use stoppage criteria to generate. That's what we're going to demonstrate in this class. We can use ensemble EMD. That we have not talked about that, but later we will. This will give you another confidence limit. That is, the ensemble is that before you do the decomposition, you add noise to it. Each experiment we do will have noise. So artificially adding noise is almost like artificially conducting different experiment. Yeah. A third way to do that is downsample. Downsampling, later we'll discuss, is when we collect data, we want to collect as detailed as you want, as detailed as possible. Yeah. So the sampling rate is the higher the better. But the sampling rate high call for resources of storage, the resource of digitizing and everything. But once you oversample, that means if I'm looking at this at the data, at the phenomena at 1 hertz, and I'm taking say 100 hertz sampling, so each cycle I will have 100 points. Yeah. That's way over. So then what we can do is downsample. Instead of use the original data, we can take the data, one data, and then skip 10 and skip another 10. This is regular skipping. Then you can also do, the downsample has a different way to do that. Like you, 100 sample, you divide it into 10 compartments, and you randomly select out of the 10 compartments of the data. Yeah. The first 10 data you can select 1. The second data you can select 5. The third data set you can select 3, and then so on and so forth. So in that way, if you decompose, if you divide the data into 10, decide to do 10 downsampling, you have the you have the 10 times 10 different kind of 10 to the 10th power, different combination of downsampling data. Yeah, then you can have an average. Of course, that's too many. So usually we don't do that. Usually we just do 1. We take 1, take 11, take 21, 2, and that. So the different, but if you take the regular sample, then it may not be independent. But if you take a random sample, the subset will be more independent to each other. Yeah. Of course, the last one is that I will change the sampling spline method. I've never tried this. Yeah. But we have indeed compared different spline, but the difference is small, so we didn't do systematic check of this. But these are all possibilities that you can generate ensemble numbers. Yeah. So recall that we have data, we take minus M1, get H1, and so on and so forth. Finally, we get this. When we stop here, this is stop criteria. And today, we're going to talk about the stop criteria. The stop criteria that I'm going to talk about today is the choice A. This A is, I call the S number. S number means that I will check the zero crossing number and the extrema number. If the zero crossing number equals the extrema and equal the same number, like for example, I count zero crossing to be 10 and extrema to be 10, then I do another time, it's also 10. Then this S number is 2. If I count 3, check another time, it's still 10, it's 3. If I check 10 and 10 and then becomes 11, I get another extra extrema. So then this 10, it's not valid, it's only 2. So depends upon how many consecutive times the zero crossing number and the extrema number equal and also equal the same number, stay in the same value. That's the S number criteria. That's the number, that's the criteria I used to establish the ensemble here. Now, you can use all the other different ways to say set a mean smaller than pre-assigned or fixed number, or SD means that you predetermine the difference between case time and k plus 1, case time and k minus 1's time. If they're different small, then I stop. But they are all valid stoppage criteria. I'm going to use this as today as a way to generate that. So to do this, we have to remember what is the S number we use. You can use S number equal to 1, S number equal to 2, and S number equal to, say, n. Yeah. And I also, in my old shifting tool, I have a maximum number of shifting. Yeah. So this maximum number of shifting is a upper limit. But you can see this upper limit really, when n is larger than a certain number, it doesn't mean anything to us anymore. So we will use different S number here to generate this ensemble. Now, in our discussion, we talk about the mode mixing, and I would again stress mode mixing. And to shift with intermittency test, so to avoid mode mixing, we have to prescribe a time scale so that we can limit the range of scale within one IMF regions. Yeah. The criteria that we got, I will use this. We talked about this before, but I will reiterate this. So here, there are some small numbers, small waves. And this small wave, if you do not take care of that, you're going to have the short waves coming out and the long waves get pushed down. And as a result, this nice wave pattern get fragmented. Yeah. And how to implement the intermittency is that when you shift, you put one more condition. You say that I selected all the extremas, and I will find the distance between each extrema. If the distance between the extrema is larger than a certain number, I will ignore those. I will only select the ones that is smaller than a certain number. Yeah. For example, here, I would select only the half wavelength is smaller than 8. Between the extrema, less than 8, then I will take. Beyond that, I will not record it as extrema. So the data will be the original data. So in this way, I use 8 once, I get this. I use 8 twice, I get a little bit, but not much. Then after that, it will be no more wave less than 8. Then I will use the regular time, regular EMD. So now, for the same data, we get these two totally different answers. This one has a very short wave mixed with very large wave. We call this phenomenon mode mixing. We should avoid this because a dynamic system, when it degenerates, this scale phenomenon, it has to be different mechanisms. Yeah. Even in a fluid mechanics situation, you have a laminar flow, suddenly get turbulence. The turbulence means instability. This means stable. Yeah, they are different phenomena. So we have to separate this from a physical point of view. Yeah. Another reason that we institute this intermittency is that with intermittency, you can control the number of IMFs that you got. Yeah, you can say that I want 10, then you can get 10. You want 11, you can get 11. But in this way, you have no control. Especially when you change the stoppage criteria, and you can have totally different number of IMFs. When you have totally different IMFs, it's very difficult for you to implement the average ensemble on IMF. You can implement it in other different ways that I will tell you how. But the number of IMF you got will be different. So with this tool, then we'll demonstrate that we can use straightforward EMD and use EMD with intermittency test. We'll compare the two and see how they are and what are the confidence limits we derive from these two approaches. We have to talk about that. If we use straightforward, the high frequency looks all right. The low frequency gets fragmented. And because the fragmentation means that the low frequency is much less coherent than the one with IMF, and the marginal spectrum. With the intermittency, we have almost more than 5 decades of dynamic range, and this Fourier we get only 2. But without that, the dynamic range is less than 1 decade. So it's very alias and the fragment cause the confidence and the resolution a lot. So this we have talked about the last time already. So the critical parameters, if we start to institute the intermittency test, we have to remember how many times we use each criteria numbers. So these numbers we have to record so that the next time you come back, you can get the same number and same result. You can repeat the result. So you can let people know that how I did it, and then people can follow your recipe to get this. So the effect of IMF is to separate component to similar scale. That's our original idea. If it cannot do that, then it defeats our purpose, like mode mixings defeat the purpose. Eliminate riding wave, no problem. Make this more symmetric, no problem. Yeah. This data, for example, if we use S number equal to 2, I count 2 consecutive times. The IMF, each IMF, the same number of extrema and same number of zero crossing, and they stay the same. So this data, immediately I get that, looks good. I get this, looks good. Each number, each component looks good. I get the 9 components. Yeah. But when you look at this, you find that they are very low frequency, mixed with high frequency, low frequency, high frequency. So we do have mode mixing here and there, but not everywhere. And the annual cycle looks good enough, looks decent, except here the annual cycle starts to fragment. Yeah, so stop criteria 2 looks good enough. Let's see if I change this, what happened? If I change it to 10 consecutive time, I get once the extrema equal to 0 crossing. I say, well, that's not good enough. I tried another time, still equal. Try another time. If this number does not change for 10 consecutive time, that means the shifting is very stable. By then, I say, all right, stop. I use 10, S number equal to 10. What happens is I get 10 components rather than 9 components. Not only that, look at the fragmentations. Look at this semi-annual cycle and the annual cycle. They're all mixed all together. So here we learn 2 things. One is that if you take a very strict stoppage criteria, you are going to get more components, but these more components will have more severe mixings. Yeah, and that's why by the time you get the 10 consecutive time, the shifting time you get maybe reach hundreds already. And so the more shifting you have actually does not guarantee you get better results. And later we'll show the theory proof by Wang Gang. Actually, if you use infinite many, you get nothing out of the EMD. Infinite many times shifting, you get nothing. Yeah. So in this way, we have a very, very poor mode mixing. See, this is annual cycle. The annual cycle, previously, the annual cycle appears the 5th. Yeah. And now, we get the 7th component. We still have annual cycle. Yeah. And if you try to average this one with the previous one, it doesn't make sense at all because it's so bad a fragmentation. Then when you average with the other IMF, it's totally nonsense. Yeah. So if you get this answer and compare with this answer, it looks totally different. Then how can you average this? How can you build an ensemble to implement the confidence limit? So the way that I do it is that I will project this answer on the time frequency space. So instead of average IMF, I will do Hilbert spectrum. Yeah, Hilbert spectrum is definitely you can average that because Hilbert spectrum is time frequency domain. Then you can define the time steps, define the frequency steps. Then you have the same number of beans. Then you can average the bean. The idea that is possible is that this annual cycle, the annual cycle is definitely there. But whether it's resided on number 5 or number 6 or number 7, doesn't matter. If I project it back to the time frequency domain, the annual cycle will still appear. This annual cycle appears here. The other annual cycle appears here, appears different places. So it should be there. The only problem I'm going to have is that in the transition, whether I create alias or not. See, this transition time, I will have problem. Yeah. So if I project this all to the Hilbert spectrum, then I will be able to do that. Before I do that, I check another thing. The thing that I check is orthogonal index. Yeah. This is the number of the maximum number of shifting, absolute limit that I said. As I said, if this upper limit is going beyond 10.5, it's about 20 or so. This is all constant. It doesn't make any difference. So the maximum number of shifting is not a critical criteria. The reason that I tried this was, as I said at the beginning of the development, sometimes we choose very strange splines. It does not converge. The computer will sit there and run for day and night. So we don't want to waste time. So we put a maximum number to cut it off. This axis is the stoppage criteria. Yeah, this is 0, 1, 2, 3. S number equal to 0, it's nonsense. S number equal to 1, 2, 3. S number equal to 1, you can see. The first time, the zero crossing equals to the extrema. The index, the orthogonal index, is almost, in here, it's almost 25%. It's very poor. So the first time you achieve the quote unquote IMF, you have to be very careful. It may not be a good solution. But when you move to second time, this suddenly shoot up, come over here. So in this region, actually from yellow all the way to deep red, from yellow always to deep red, it's 0.05. It's acceptable. In fact, I would accept the 0.1 to be more generous. Yeah, but the blue is not good enough. The orthogonality index is very bad. So I would discard this as a valid IMF. Yeah, I'll only keep this. So when you keep this, then you can see that whether you use 1 or 2, this has a topography in that. Then you can see that by choosing different stoppage criteria, you actually have slightly different orthogonal index. And to show you more detail, then I cut lines at each maximum. And then you can see that when this is 1, 10, 20, 30, 40, they fluctuate a lot. By the time we get to 100, 1,000, it doesn't make any difference. Here, I shifted each number by 0.01 so that they can see the difference. So after 100, it doesn't make any difference of what you choose. But for the low number, if you say that I shifted 10 times, I stop. This is what the Zhaohua Wu advocates. Yeah, you can see the 10 shifting. It's still pretty rough. Yeah, but the moral is, the lower the number you shift, the more original property that you retain. Yeah, even though the orthogonal index can be poor, but the orthogonal index poor only when you impose very high stoppage criteria. If you stay in this region, they are doing very well. See, this is 10, maximum 10. It was 10. Whether you satisfy or not, I don't care. 10, I stop. Yeah. So when the 10 stop, it's not too bad. Yeah, the orthogonal index is 0. It's very good. So there are, of course, other reasons that Zhaohua, Dr. Wu select 10. We'll talk about that when we come out to the ensemble. So 10 is a good compromise. And if you use other than 10, use 20, 20 is still good. But if you use more and more, So actually it starts to fluctuate. Yeah. So higher number of shifting is not, in general, not good. Yeah. We should keep our shifting number as low as possible. Yeah. Now, because of that, Zhao Hua picked 10. Forget it. I just used 10. Yeah. So this is the very detailed. This is the detailed way to show the previous. I cut sections here, cut sections, the last cut section at 1,000. You have this kind of data. So this we can see that the lower number of maximum shifting coupled with low stoppage criteria actually give you very nice answer. This is 3 up to 30. They are all very close to orthogonal. Yeah. So we keep that in mind. When I first developed this method, I give to a colleague of mine. She's a very, very smart person, very meticulous, pay lots of attention to details. He said, well, if the difference is small, I should be better. So he put the difference to be 10 minus 6. She shifted 1 million times and get totally nonsense answers. Anyway, so now we can see that through this shifting, we get a different answer, whether with or without intermittency, we can get a spectrum at least. Then we can average the spectrum. Average spectrum, this is the spectrum that we got from 2. Yeah, without the intermittency. We get the half monthly, half yearly cycle. Yeah, it looks, especially over here, looks very diffused because of the data. It's very good. There's lots of noise. Yeah, we get so much details in the data, and if we selected all the data with all the different stoppage criteria, we finally get the average. This is the average. Yeah. Remember, when we have different stoppage criteria, the IMF is so different. Yeah. But finally, when you average, it looks almost the same. You compare this with that. You see the difference. The only difference is that here, even the annual cycle is fragmented. But if you average them, this is the annual cycle. Annual cycle showed up better. So this is a mean spectrum. This is the standard deviation. This is the standard deviation, and the spectrum looks almost the same. Yeah. Wherever you have number, you have difference. Wherever you don't have number, the difference is small. Yeah. Now, how to judge this is good or bad? We'll look at to guide our eye to get a value. I use the marginal spectrum. In other words, using this spectrum, integrate the timeout. And after you integrate timeout, you will see this is the spectrum. This, the blue line, is the RMS, the data plus minus 1 RMS. So you plotted out this. This is the data. This is RMS. Yeah. This is log. This is actually linear. So this data, even though the difference is small, but the difference is very large in the linear scale. And so this is how after all the mode mixing, all different IMFs, you actually can get a coherent mean and the standard deviation. Not only that, if you take each component, there are 10 different IMFs I get. I use stoppage criteria S equal to 2, 3, 4, 5, all the way to 10, 15. The 10 different average, 10 different individual realization give you very close answer at the peak. And and for the monthly and the half monthly, it's also very coherent. And it's over this region where you don't have a lot of data, you have large differences. And here you get large differences. Yeah. These large differences actually were generated by the transition between different scales. Yeah. And this is the 10 different case. This is the average. This is one standard. This is 95 confidence limit. This is 2 standard deviation away from that. So most of near the peak, the value are very reliable, even if we have all the fragment mode mixing. Yeah. All right. So how about with intermittency? With intermittency, then we can control the number of IMFs. So this is, I use S number equal to 2, maximum shifting 100 times. Yeah, I use 4. Use 4 means the short wave, beyond 4 I will not look at it. And half wavelength. So what I pick out is that on the data, I do have certain section, I have a very, very short wavelength. What are those short wavelengths? Those short wavelengths are actually caused by storms. Yeah. When we have large storm system on Earth, the storm system actually caused the angular momentum of the Earth to change. So the rotating speed of Earth will change slightly. Now, why it only appear here? Because we appear here because the data is better. Over this side, the data are averaged many days. And those are more instantaneous data. Only by then we can pick out the influence of storms. Then we have the half monthly, the monthly, and half yearly and yearly. This is S equal to 2. And we have 11 components. The last component is 0. Yeah. And we can have stop criteria S number equal to 10. Here you can see the equals to 10. There are some fragmented thing because I can control now. Then I make this half yearly appear here. I make yearly appears here. Yeah. This is 7. So if you look back, I can control this half yearly to be 7 by manipulate the intermittency criteria. You can force this component to appear here. You can force the component appear there. Yeah. You can set a 0 line there. So in this way, the stoppage criteria 2, the stoppage criteria 10, they all give you the annual cycle, half annual cycle, monthly, half monthly. You see, if you use 10, then you get a lot of more storm influences. Yeah. But the total number is 12. Yeah. So by this way, because I have the same number of IMFs, then I can average, in addition to spectrum, I can average IMFs. So you go through 2, 3, 4, 5, 10, and all the numbers, then you can see that for the different shifting, you will have the envelope of the annual cycle 2 times, 6 times, 20 times. They fluctuate. Yeah, there are fluctuations. And orthogonal index for the shifting with intermittency. This is 0.1, this is 0.1 minus, and this is 0. They roughly are all below 0.1. So that's the criteria that I have. If the orthogonal index is more than 0.1, more than 10%, I will I will check my shifting. Yeah. So all the numbers start from 2, s equal to 2. They are all around around 5 or 6. And if you average, because I have the same number of IMF, I can average to get yearly. I can never get a half yearly, get the monthly and a half monthly, and so on. So in this way, I get the average mean of all 9 cases. Not only I can get a mean, I can get the standard deviation of the 9 cases. The standard deviation, you can see, is very, very small. The standard deviation of the storm is high because the storm does not occur all the time. The standard deviation of the half monthly and monthly, or half yearly are very small, except that at a certain location, they are high. We're going to talk about that later. So in this way, we get the mean value for IMFs and standard deviation for IMFs. And if you look at the spectrum, the spectrum here, this is monthly, half monthly, this is monthly. Compare this with the last one. This is much cleaner because we have already rejected some of the noise. Yeah, noise is way beyond 40. The noise is typically 5 to 7 days. Yeah, it's very high frequency noise. The frontal movement typically around 5 days. Yeah, so the monthly appears, half monthly appears better, monthly appears better. The most shocking thing is this annual cycle appears totally like a straight line. Whereas before, let me see if I can find it before. This is the mean. Look at this annual cycle. This annual cycle, over here, over here, over here, they're all fragmented. Yeah. Even though this fragmented, it still gives you lots of good information when you look at the marginal spectrum. But compare that with this, you see the annual cycle. It's very clear. Yeah. Half annual cycle fluctuates. That's not because the answer is no good. Later, toward the end of the course, we will talk about this fluctuation. This actually represents a nonlinear wave, the degree of nonlinearity. So this is the mean. This is the standard deviation. See the standard deviation along the annual? It's very very small. Now, and if we integrate everything together, you will see this is the marginal spectrum. This is the standard deviation, and if we presented all 9 cases, and we have a mean, we have a standard deviation. You compare this number with the previous number. Let's see if I can plot it. Everywhere, annual cycle, half annual, monthly, half monthly, they're all very, very tight. And if you presented, if you compare this with the previous, this is without intermittency test. This is with intermittency test, without width. Concentrate in this area. Yeah, this is this is with confidence limit. This is, oops. This is with confidence limit. This is without confidence. With, without, with, without. What happened is that the peak here is much higher than the peak here. So with confidence limit, by eliminating the potential mode mixing and the alias caused by the transition, you actually get a better resolution on this peak. Yeah. For over there, you don't see a lot of difference. The difference is very small. Yeah. So in this way, we got a spectrum. We get a spectrum that we can believe. We get a spectrum not only we can believe, we have confidence limit established for the marginal spectrum and all that. And if we look at the individual components, this is the components. I plotted all 9 components, 9 different trials of the annual cycle. I plotted over here. Remember before I plotted the envelope. The envelope looks so different. If you plug everything together, you find that all 9 cases all fall together. At least in the time space, the frequency are reasonably good. Let me guide your eye to see where the difference occur. The difference occur over here. The difference occur over here. Here you can see some line skipped, and here you also see some line appears here. Yeah. Around between 1990 and 1995, and between 1965 and 1970, we have problem. The standard deviation is very large. It turns out, if you expand it out, you see the 9 different cases. Some are very nice, except 2 cases stand totally different. Yeah. It turns out, if you check the NOAA website, you'll find the NOAA website talk about this particular region as a very unstable El Nino year. And this happens to be 1990 to 1993. I remember clearly in 1992, 1993, Mark Ken from Columbia, Lamont, claimed that he can predict the El Nino. The El Nino happens every 2 to 7 years. Yeah, it's a oceanographic phenomenon that the equatorial ocean suddenly gets very warm. It's called El Nino. To this day, we can predict El Nino very nice by the scale, but not very accurate in phase. In other words, when it will happen, we cannot tell. But we will produce a statistics. Is what the average period we can do that. This is how much we know about the ocean. Very limited. Beyond El Nino scale, our prediction ability is almost nothing. Yeah, like 20-year cycle, 60-year cycle, we cannot predict. So in 1992, Mark Ken said that he can predict El Nino, and it happens that he made a claim. He has a bad luck picking that year. If he picked this year, he will be right. Yeah, he picked this year, and El Nino just has a big anomaly, and this anomaly turns out to be the one that we have a very large uncertainty. Yeah, so that indicates that this simple method gives us all the physics that we want to know. When the phenomenon is ambiguous, our anomaly is high. When the phenomenon is not ambiguous, our anomaly is low. Yeah. So here is the annual cycle. On the dotted line, I plotted where the standard deviation is high. That's 1993, 1992. over here we are very uncertain. Over here we are relatively uncertain. Yeah. Now this graph I have discussed in the introduction. This is annual cycle. Annual cycle are not uniformly large, and they are high numbers and low numbers, and these are caused by the El Nino events, and the El Nino events because of the warm equatorial water. It gives the Earth's rotation a extra angular momentum, make the rotating slower and faster, slower and faster. Yeah. So this actually is the annual cycle. The annual cycle, if you look at the detail, the annual cycle are very different. Yeah. These are different cases of envelopes. And this is the average is what I plotted in the last view graph. Yeah. And this is the standard deviation over here. Look at it, the envelope difference. Yeah. Over here it's also very large. So what do we learn from this? We learn from this is that we can actually establish a confidence limit. We can feel good about what we got. We could feel confidence about what we got. But a extension of that is to find the optimum sifting criteria, sifting parameters. The moral is the maximum sifting number should be set very high to guarantee that stoppage criteria is always satisfied. Yeah, that was the view I had it before, but now I'll modify that, especially in light of what Dr. Wu did. He said, forget about the large number of sifting, just set it 10, forget it, okay? So, but this, if you select a stoppage criteria, and if the criteria is very stringent, and if you set a large number low, then that criteria never be reached. It just stop at 10. Like in our case, when we set the maximum number equal to 10, it did not get to the number. It just stopped at 10. So that basically is the 10 times sifting result that I present. The stoppage criteria should be consider individual case, and there must be a range that it's optimal. Yeah. Let's see how can we see which one is optimal. So the value we got, we can get the average value. Yeah. Each time we try, we can get the average value. Then we can also try to see the average value versus the individual case, see how large the difference is. Now the logic here is that if this number is small, means that what I got is near the mean. Since I trust mean to be the truth, therefore, whichever number is smallest means I'm closer to the truth. Here, I'm treating the mean as truth. Treating mean as truth. Yeah. So in this logic, with this assumption, then I can look for the the best sifting. Here is the stoppage criteria, and I computed the difference, like I defined here. Okay. The average value minus the individual case squared. So here's what I got. If I use stoppage criteria 2, the difference is very large. 3, it's getting better. 4, you get small. And after 4, it stay about the same, and eventually it picks up. Yeah. So if I want to have a value near the expected value, I should select somewhere around here. Yeah. So the stoppage criteria using the intermittency, it's around 4, 5, 6. And if now this actually this is for annual cycle. For half monthly, it jump up and down and eventually settle around here. So it's around 4, 5 or 6. It's good. This is half monthly. This Hilbert spectrum. The Hilbert spectrum after 2, 3, 4, it's around this region which has a minimum, and beyond that it's pick up again. So in this case, with this, I think that we should select somewhere around this number. But I also know the lower the better. So with this, then if I choose S, I will choose either 2 or 3. I'm not going to choose 5 or 6. Yeah. So this way, we establish a very rough optimum range of the stoppage criteria. And that is if you use stoppage criteria. And stoppage criteria, for a while, over the last year or so, I start to try to give up the stoppage criteria because stoppage criteria is superseded by Dr. Wu's work of 10. Yeah, 10 has other advantages, but now when I look back, I find that the ensemble has its limitation. So if you really want to have a different kind of view based on different problem, perhaps you still should pay attention to the stop criteria. And when you use stoppage criteria, use as low as possible, not use as high as possible. If you're not sure whether you use the right or wrong, try more than one and average it. Yeah. And in that case, only in that case, you will feel more confident. Hilbert spectrum without the intermittency, it's 4, 5. So choose as low as possible. Yeah. But after 4 or 5, it just stay pretty flat. Yeah. This is, I only use one set. Whether this set represents everything or not, I don't know. Yeah, there's no way that you can generalize this. This is a very specific example. So now I try another case to see whether this has any universal property or not. Here, I use the earthquake record, GG earthquake, the station 921. This is the largest acceleration that ever recorded during GG earthquake. It's almost get to 1G, minus 1G. But I was told this station has a problem. Xiaolan, you know this, right? Is this station has a problem? I heard that this station actually failed, and then the instrument dropped. And in that moment, its acceleration is G, 1G. Yeah. But anyway, when I first get this, I used this data a lot, so I still use this data. This is the GG earthquake. It's a very huge, largest earthquake Taiwan has on record. Here is the Hilbert spectrum of GG earthquake. First, you get this. What you call the compression wave, and then that's the up here first, and then you suddenly shift it to the shear wave and all that. And you can also see this wave has a little bit of dispersive relationship, yeah, and the frequency change. Anyway, so this is the mean Hilbert spectrum I derived from the GG earthquake by using all different kind of stoppage criteria. Yeah. Then once you get this spectrum, this is the average spectrum. That means after I try this, try that, and try many, many different times, I get this. And when you plot up, I tried 1, 2, 3, 4, all the way to 20. And it gets a general shape like this. So here, 2, 3, 4 are all pretty good. By the time you get 4, it's minimum. Then get up and down. So based on the criteria that the lower the better, I would definitely select this part as my stoppage criteria. So the stoppage criteria, that based on this is a very, very different case compared to compared to the length of day. We still get a general shape of a ball-shaped answer. That's comforting. That means if you shifted it very, very detailed, you're not going to get anything better. Yeah. But if you do not shift enough, it's not very good either. Yeah. Somewhere you'll get a good answer. In the ensemble EMD, I keep referring back to ensemble EMD. We use 10. We've never checked whether 10 is a good IMF or not. Okay, but using ensemble, at the end we know it's not IMF. So if you check with this, all the components will probably flunk the stoppage criteria. So with this, from the above test, we can see that the Hilbert spectrum difference is less sensitive to change stoppage criteria than S number, criteria S than IMF. IMF is very sensitive. If you get a slightly different stoppage criteria, you get a totally different mode mixing picture. So it is impossible for you to average IMF, the individual components. But for spectrum, Hilbert spectrum, you can still get a decent average because Hilbert spectrum has the fixed beams on time and frequency slots. Now, from IMF tests, we suggest the S number should be around 3 to 10. So in general, the lower the S number should be preferred. So when I do problem, I will never use more than 3. Seldom I use 4. I usually use 2 or 3. Yeah. These selections in agreement with our experience, but the other data should be tried. Typically, when you have more noise and more intermittency, then we'll have more problems in selecting the stoppage criteria. Yeah. But from this, we can see, even if we cannot average IMF, we can still average the spectrum and get an answer. So the confidence limit present here is only for EMD method. Yeah. As at the very beginning, I said there are many different possibilities. Yeah. Using stoppage criteria is only one of the ways. And recently, increasingly, I've tried to use downsampling to build a confidence limit. I think downsampling is a good practice, provided when you're taking data, you have take enough data for you to downsample. Yeah. In most cases, if you downsample, you will get a much better answer than use the full data. The total data can give you very detailed information, but when you compute, but you have to also realize, the more data you got, the more detail you got. When you take a derivative, the noise actually get amplified. Yeah. So in in computing instantaneous frequency, downsample sometimes give you much smoother answer. But the downsample, you have to be careful. You cannot downsample too much. Make sure that each wave get around 10 points. That's my rule. Yeah. At least the phenomenon that you want to see, you don't want to, it has less than 10 points. Yeah. So we can use different. You can use stoppage criteria and different method. And downsample is the one that I'm using a lot. So most interestingly is the ensemble EMD. Yeah, and ensemble EMD is the method that we're going to discuss in the next section. The next section we're going to discuss ensemble EMD, but there are some preliminary for the ensemble EMD discussion, that is to study the white noise. Yeah, so we will do the next. We'll stop here for this class. Next time we'll talk about ensemble EMD. Any questions? A colleague in Tokyo, have any questions?
Oh no.
Yeah. Let me ask you, do I speak too fast?
No, it's okay.
Okay.
It's okay.
All right, and you can hear clear, right?
Yes.
Yes.
Okay. By the way, since you are here, I'm entertaining the idea of come to visit you. I will give a couple lectures in person in Tokyo, so that it will be have even opportunity to see how poor I perform in person.
That's not true. We're looking forward to.
Okay, so I will write you to set up the schedule. Before the end of the semester, I want to see see you in person. I've teach this course. This is the third time to Japan, but I've never been in your classroom and see the people in person. So I'll try this semester. Okay.
Okay.
It'll
All
be
right.
an honor to have you.
Sure.
Goodbye.
All right. The class is dismissed if you don't have any question. Right. Bye bye. 好，关掉。Now we can switch to Chinese. 有没有人要问问题的？用中文？有没有人问问题？
我想问一下那个 stop criteria 那一张，
对。
那个为什么20到24的时候，它没有，它跟原先开始一开始是都没有很好，就是第二次或就是做2次或4次是比较建议的。
对，你说
对，
你说到20次为
对，
什么不好？
它其实2到4个其实蛮不错的，但是后来这个跟资料量的大小有关系。
不，这个我这个地方我没，你问这个问题问得很好啊。为什么说问得很好呢？你看这20一下子跑出去了啊，2啊、3、4啊这边都蛮好的。为什么这个20跟14一下子跳起来了啊？这个地方啊，是我做这个工作的时候有一点 flaw， 有一点缺陷。这缺陷很少人指出来，小英指出来了。什么呢？就我这边 take 的 sample 的那个不 fair， 你有没有看见我的 sample 不 fair？ 我在这里 take 好多 sample， 在这里 take 很少 sample。假如我每一点都 take 的话，说不定这也下来了，你懂吧？因为这个它在附近都没有点嘛，我这个附近都有点，对吧？我假如每一点我这个我11、12、13、14我们都 take 的话，这边的 sample 会多，所以这边可能也会下来。所以这边是不是真的在那里，还是一个问题，对吧？我当时做的时候没有仔细去做这些。我假如现在做一个100，这个100的一定跟这个不一样，对不对？但是100跟101很近了。但是我现在在这个 average 里面，我做了20以后没有做19啊， 20一定跟这个不一样，但是20跟19是很近的，所以我把19也摆进去，21也摆进去，18也摆进去，22也摆进去，这个一下就下来了。就是它对 mean 的影响就大了，对不对？现在它对 mean 的影响太小了，这个开始对 mean 影响。我假如 to be fair 的话，我应该我说5个一个，我那里是15，这里5，这里我只 take 4个的话 ，average 可能跑这里来。那么，所以那个20是高的，不一定是20是高的，是因为我这是一个 artifact。
是跟上一张另外一张的
另外一张。
这个
也一样，
这个就是它就比较
对，这个不同的题目不同啊，这个我们这个里面你再加了点的话，恐怕也差不多。就换句话说，这个题目跟上个题目两个题目不一样，题目不一样呢，这个题目呢就是到了4以后它就平了，但是上一个题目到了4以后它不平呀，但是是不是多不平我也不知道，因为我上一个这个是我。这里面有一些统计上的问题，我当时没有注意呀。这个不是一个 fair 的 sample， 对不对？就等于我在这里，我扛大一个铺，我在这个 class 里面每个人都问，到了外面就问2个人，我说这个是 average of the school of the whole university， 是不 fair 的，因为我在这里面取的太多的 sample， 那边取的太少的 sample。那当然嘛，跟 sample size 有关了，呀，所以那个 sample size determine 你的 standard deviation， 也就 determine 你的那个 confidence limit， 对不对？但是这个 sample distribution 也是要紧的。我在这边非常 dense 的 sample， 到那边非常不 dense 的 sample， 这个不 represent the whole thing， 这个只是一个 schematic。我在别的地方我都没有承认错误，只有跟你们承认错误。啊，我提的好啊！我本来打了马虎眼就算了，其实你这样一提，大家都知道了，所以你们下次就不会犯这种错，啊。这个错我也没有再到别的地方去讲，你发现这个 paper 被人家晒了几百次。呀，还有什么问题？好，那我们就谢谢。今天我们早了10分钟下课啊。
我今天猜错你走的路线。
啊，我今
说你会从中心出发。
那我今天
他们说你从家里出发。
我哥哥来了，我就从我家里出发。OK。你们要多问问题啊！您讲不问问题，我有时候我